So this is our in some sense the first lecture on how the signals propagate on the wireless, and what we will talk about is how the signal is reflected, diffracted, scattered, what is fading, shadowing, multipath, etc., etc. So as you know, this is the second lecture. The first lecture was about things that we had covered in 473, which was the last lecture, and we will use all of that to understand this one. So wireless radio channel is actually somewhat very similar to the light propagation. Okay? And if you have a flashlight and you turn it on, you know the light intensity goes down as the light progresses, right? And also the area it discovers actually goes up because the light goes in all directions, right? Same thing happens to the wireless, except that you cannot see it. If there is something in between, the light can be blocked, and same thing happens to the wireless. The wireless can be blocked, except that wireless signals do not just travel in a straight line, so they can go around the buildings. Although you will see the effect, but they can go around the buildings. And just like light, there are other sources of wireless that can interfere and cause noise. There are many things that we'll discuss actually throughout this lecture, but first thing is the path loss. Path loss is that if you send out 3 dBm or 1000 dBm power, it will become less and less and less and less as it goes. All right. Noise, we talked about that. It will be added to the signal as you travel. Shadowing, and the shadowing comes right from the light. If there is something in the middle, it will cause a shadow, right? That means there will be some area where you won't have any light, right? In the case of wireless, there will be some area where there will be less wireless, not zero, but there will be some less. Shadowing, frequency dispersion due to Doppler spread, and if the things are moving, either the receiver or the transmitter, it doesn't matter who moves, then there is a Doppler shift. Interference by different transmitters and also in the same transmitter, as you will see. Multipath, and that is the reason that the signal can go in many different paths and they can interfere. And then inter-symbol interference. And then what happens in wireless is that you might send 2 symbols and they might become 1. And we'll see why and how. All right, first thing, antenna. So normally if you have an antenna, it sends out the signal in all directions in 3 dimensions. So you get a sphere. If you have an antenna, signal will go up, down, left, right, bottom, everywhere, right? Now if you send out a certain amount, let's say 1 watt of power, which generally we'll say 1 watt is like 1000 dBm, you send out, then that power will basically be spread out in a sphere, and you can calculate the area of the sphere, and as you go farther and farther, the area will go bigger and bigger, right? And so the intensity of the signal would be less and less. And if you have the same size antenna, as you go farther and farther, you will get less and less of the signal. Okay? You can just think in terms of light. Exactly the same formulas apply for the wireless. Is that the signal is going in a sphere, and you have an antenna. Depending upon the distance, you are covering very small part of that sphere, and so you are getting very small part of that signal. So if to increase the signal in power, you really either need to use big antenna, or you need to come closer to the source, or increase the power from the source. So anyway, so the transmitter, so this one is actually called isotropic. Isotropic means the signal strength is same in all directions. But most antennas are not isotropic. And actually, so if you really measure it, you will find it very close to the circle and spheres here. But most antennas are not. You will find that the signal strength is more like this, where what I have done is I have drawn a line at equal power. So if I found the power, let's say 1 watt per square inch, I just went around until I got 1 watt per square inch. So this is the line. If you go beyond this, it will get less. Inside this will be more. So anyway, so this is what we call the antenna's footprint, and you can see that even if you are in this direction, you can be far away, but you get almost the same power as if you were here, but very close. Right? So this is a directional antenna. Right? This is a directional antenna, and it is directed to this in this direction because it really wants to transmit in that direction. Maybe the receiver is in that direction. So you can design a directional antennas, and most antennas are designed to be directional. And since it is directional, then we measure its gain. So we say, oh, this antenna is better because I can get more power, in that direction. So basically, the formula for power is, and now again, unless we specify, the power is generally in watts, okay? And we keep converting between watts and dBms and things like that. So if there is a multiplication, you know that it is in watts because you don't multiply logs. So here is power received, PR, is equal to power transmitted, PT, times the gain of the transmitting antenna. That means how much more than the isotropic you can get. Okay? So it is 2 times the isotropic, then gain is 2. GR, receiving antenna. So receiving antenna can also be exactly like that. Okay? It may receive more from one direction than from the other. Okay? So you can have isotropic receiving antenna, or you can have a directional receiving antenna. If you have a directional receiving antenna, then you have a GR as the gain, times lambda, and lambda is the wavelength that you are transmitting, divided by 4 pi d whole square. So d is the actually it should be radius somewhere, but the term d is confusing me. So anyway, the d is the radius of the basically distance. You can say d is the distance actually, right? So which is the radius of the sphere that we are talking about here. Is that clear? What is d? Yeah.
GR is gain of the receiver.
GR is the gain of the receiving antenna, and GT is the gain of the transmitting antenna. Okay, so now let's see. We covered everything. The same antenna is used for transmission and reception. So generally you have only one antenna like you have, and the transmitter might have one antenna. Omnidirectional is this one, isotropic, and directional is that one which is in one direction, and therefore it has a gain with respect to the isotropic antenna, and all these ratios are measured in dBs. So although when you put it here you will multiply by the number, but when you express you say dB. So if you go to buy antenna in the store, they will say this is a 7 dB antenna. The right word is 7 dBi. I is for isotropic. So that means is that this antenna gives you 7 dB more power than an isotropic antenna. Now 7 dB is, you can convert that into the 10 raised to whatever 0.7, and that will come out to the ratio, how much more power it is. Okay? So let's see. Now lambda is the wavelength. So now one thing you notice is, since the wavelength is opposite of frequency, that the power goes down with the frequency. Now this is very important to know. This is one of the fundamentals, is that if you want to go very far, you want to use lower frequencies. Alright? So, for example, if you are given a choice of using 2.4 and 5.8, Which one will go farther? 2.4 gigahertz and 5.8 gigahertz. Both are allowed in Wi-Fi. Which one will go farther? 2.4. All right. And so that is just natural. People like to use smaller frequencies. 700 megahertz would be even better than 2.4. And 300 would be better than 700, and so on and so forth. And obviously those lower frequencies are not available, or are not enough available. Okay. Second thing you notice here is that it goes down by the distance squared. So if you go twice as much, the power has gone down by a fourth. Okay. All right. Now, what happens to the power? So if there is a radio transmitter here in this car, and it is going in a street, there is a pole here, there is a post, lamp post. Some of it will be reflected from the buildings. Right? So even though the buildings don't have any mirrors in them, but for wireless they act like a mirror. Okay? Some of it will be diffracted. It will just change the direction like that. Some of it will be scattered, in all directions like that. So there are many different phenomena that will somehow get the signal here, even though you cannot see from here to here. So light will probably not get here. Light can get reflected if there was a glass or mirror here, but wireless signal is reflected by everything. So you will get some signal here. Okay, and so those are the terms. As I said again, basically in a wireless communication course, they go into the mathematics of all this. So there is a lot of mathematics that we are skipping because we really don't need to know. We just need to know the phenomena, and so that we can concentrate on the networking aspect of it. So the reflection. Reflection is when the surface is large relative to the wavelength. So remember, 2.4 gigahertz is what is the wavelength? Anybody remembers that? 2.4 gigahertz, we calculated the wavelength right here in the class. About 12 centimeter. Right? So if the surface, if you have something larger than 12 centimeter, which is most of it, it will be reflected. And if there is an edge, it will be diffracted and may receive signal. And so basically all it is saying is because of the diffraction, even if there is no line of sight, and because of the reflection and diffraction both, and because it is scattering all of these, there is no line of sight. There is no straight line that can come through, but the signal will be received. Scattering when it is the order of the wavelength, so it is 12 centimeters or less, and if the line of sight, diffracted and scattered signals are not significant, reflected signal may be if no loss. Okay, so don't worry about all of that. Basically, so the idea is because of all three different things, sometimes we don't realize that the signal is all traveling in a straight line. Where did it go? Backspace. Oh, yeah, signal is traveling in a straight line, but because of the reflection and diffraction and scattering, etc., you get it in places where there is no straight line available. All right. So the next concept and the next word we use in wireless is channel model. Again, there is a lot of mathematics behind it, and if you go back to the references which I have not put here, and so actually there is a reference on this one, channel model. There is a lot of mathematics even in that one. So, but basically the idea is that when you transmit and when you receive, this is the channel. The channel is basically the wireless channel, the media in between. And the channel has a frequency response. Okay. So what we say is that the received frequency spectrum YF is a function of the transmitted frequency spectrum XF times HF, which is the frequency spectrum of the channel, or actually frequency response of the channel, plus NF, which is the noise. Okay. So now these are some complicated functions. We multiply them and do all that function when we do some wireless channel modeling. Again, we will not be doing that in this course. But you just have to know these words, because whenever you work with the wireless people, which I did quite a bit, they always use these things. Channel model, and reflection, scattering, so on and so forth. So since you are taking a wireless course, you need to know this thing. However, this part requires a lot more time and mathematics than we want to do here. But you have to know basically what it is that the channel response and the transmitted response, they multiply to get you the output frequency response. Okay. And coming back to our previous formula that we already talked about, PR is equal to PT times GT 1 upon 4 pi d square AR. AR is the receiving antenna area. So what is happening is whatever power is being transmitted, it is being distributed to a sphere, and the sphere area is 4 pi d square. All right, the symbol is D, but it is the radius, right? D is the distance. So 4 pi d square is the square area, right? If you just put an antenna which has an area AR, right? So then you will get only AR upon 4 pi d square power. And by definition, the definition of the antenna gain is 4 pi upon lambda square AR. And therefore, the previous formula, that's how we got the previous formula. PR is equal to PT, GT, GR, lambda upon 4 pi d whole square. And the guy who first wrote it is, I think it's called Fries. I'm not sure. Fries, whatever. So that is the law. This is the formula. Basically, you multiply all of this, and that is called the path loss. So you send some dB, some watts, and you get some other watts, and the rest is the loss. This multiplier is the loss. We will be doing all of this in, let's say, in log scale. So you have some dB power sent, dB power received. The difference would be the path loss. Any question about any of this? All right, so let's see the multipath. What happens with multipath? So here is the transmitting antenna, here is the receiving antenna. This actually shows a television antenna, but anyway. So what happens is the signal comes directly as well as by reflected through the building. So you get two signals. In fact, you might get many signals. You send one pulse, you might get 4 pulses. One pulse straight through, another pulse after reflection, and therefore it comes little bit later in time, and maybe even smaller. And the third pulse takes even longer path, comes even later in time and even smaller. And the fourth pulse goes somewhere else. So you get, from this pulse you get these many pulses. So basically, the channel is like a tunnel in which you send people who are very beautiful, handsome, tall, thin, and as they travel, they get two things. First of all, they become fatter and they become shorter. All right? And if you think of it that way, then what will happen is you send a very tall, thin pulse, two of them. When they come out, they are very fat, very wide, and very short. And in fact, if they travel for too long together, they might just merge into each other. I mean, like they start pressing into each other. So you can't really send too many of them. Right? In fact, there is another phenomenon in optical. I use the same coding in optical. And there you might even get more than you send 2 and 3 come out. So, you know, all those things. Anyway, so the idea is that because of this multipath, there is inter-symbol interference. So you send 2 symbols and they start running into each other. So you really cannot distinguish between the 2 symbols because here you don't know which symbol you are receiving. Right? And so this is called inter-symbol interference, and we have to design ways, and this basically limits how many bits you can send, because if you send too many bits, they will be very close to each other, and you will be in trouble. So basically, inter-symbol interference resembles this thing, okay? And again, if you want to see technically what it is that you send 2 pulses, and each pulse becomes multiple pulses. So this one became 4, and this one became 4. And then they start running into each other, right? So basically you have to somehow worry about what to do for the inter-symbol interference. And since this is time, we call it delay spread. So this is how long the pulse became. Your pulse was 0 bits actually here, and it became so big, so wide, right? And the fading is called the fluctuation in the amplitude. So basically, any reduction in the amplitude, any change in the power is called fading. And multipath may add constructively or destructively. So that's the thing, is that it is possible that it may help you. It is possible that it may hurt you. And we'll see in a minute as to how that happens. So here is an example that this is an antenna, transmitting antenna, this is a receiving antenna. So some signal comes straight and some signal comes by reflection to the ground. Now again, in wireless communication, what they can do exact mathematical modeling of this, and they call it 2-ray model, because actually signal is not just going into 2 rays, it is going into many reflections. Right? But if you just do simplest 2-ray model, 1-ray model would be just go a straight line. 2-ray model is just use one more reflection in the middle. If you do that, then it will come out that the received power is PT, GT, GR times HT, HR upon D square whole square. HT is the height of the transmitter, HR is the height of the receiver. Okay? So how high you are, depending upon that, you get the power. Now, it's valid for distances longer than some amount. So before that, the formula is different, but after D break, this is the formula. D break is the distance, 4 times HT plus HR upon lambda. Before that, the formula is slightly different. So after this thing, the power becomes independent of frequency. That's another thing that interesting is that there is no, basically, then it becomes independent of frequency, and notice that the D has a power of 4, minus 4. People have done the measurement to verify these things, and they found that the power is actually 1.5 to 5.4, but 4 is the number that generally people use. So this is called D raised to minus 4 law. So as normally you would think that 4 pi d square, you have, but then there are other things which have to be done, which is the reflection and everything else has to be added, right? And that makes it d raised to minus 4. Without the reflection, if you just think about a straight sphere, that gives you d square. But when you add the reflections, etc., it becomes d raised to minus 4. And the actual number could be somewhere between 1.5 to 5.5. You really have to go to the area, figure out what is the, how many buildings there are and things like that. And basically people do lots of measurements and then they install their antenna. So fading actually simply means changes in the power level. And the changes in the power level could be basically it's a variation. It could be little bit high, little bit low, little bit high, little bit low. So when you measure it, you won't get just a straight decrease. Sometimes you will get increase, decrease, increase, decrease like that. Because there is a randomness. So now what we do is, for the small amount of randomness, we call it small fading. For large amount of randomness, we call it large scale fading. Okay? So shadowing is the large scale fading. If you have a big building in front of you, then it will cause a large amount of variation, and that is called shadowing. Okay? So here is the thing. You will see the receive power here, you measure, it's kind of very high, and then suddenly because the building power is 0, and then it might come back from the behind. So if you plot the power loss, a path loss, this is how it will look like. You see there is a very thin line here, which is actually the line that I want to show you. Very thin line, and if you ignore that small scale fading, then you get this thicker line, right? And if you ignore all this oscillation, then you get this straight line. Okay? So that little but thinner thing that you see here, that is caused by multipath shadowing, etc., etc. And the dotted line is caused by shadowing in path loss, and this is the path loss. So this is straight path loss. When you add shadowing to it, you get this, which is the large scale fading. And then when you add the small scale fading, you get small variation like that. Okay? And all of this, people calculate and do all this kind of statistics on this. We just need to know this thing and so that we can plan accordingly, but really we won't be doing any calculations like that. Another concept that you need to know is Fresnel zones. And the Fresnel zones is the idea that when you have a transmitter and the receiver, the signal actually travels in many directions, paths, and even if it is open space, total open space, and nothing to reflect or anything like that, it really travels in multiple paths. And I mean, maybe it is because of the atmosphere or something like that. But anyway, so the idea is that if you draw an ellipse with the focal point at these two points, you know how to draw an ellipse? I mean, some of you might have done this exercise in high school. If you have to draw an ellipse, you take a thread and then you put a pencil right here, and then you just go around. You get an ellipse, right? So the thing is, if you take this ellipse, the ellipse for which the run length is line of sight, which is this one right here between the two, plus I lambda by 2. Lambda is the wavelength. I could be 1, 2, 3, 4, 5. So you take line of sight, which is just not an ellipse, it is just a straight line. If you take I equal to 1, then you get this ellipse. Then you take I equal to 2, you get a second ellipse. Take I equal to 3, you get a third ellipse. The more ellipses you have free without any abstraction, the more power you get. Alright? So here's the idea. Suppose you take two antennas and you put them here 10 feet around here and you measure the power loss. Then you take the same two antenna and you take them outside, the power loss would be different simply because there is more space for the signal to travel. If you take it up in the sky, it will be even more power will go through. Now you wonder how come more is going through, because it is less abstraction and basically more ellipses can be covered. Okay? So the height of the antenna makes a difference, and that's why most of the antennas are mounted on the mountain. I mean, on the tall buildings, on the top of the buildings. Okay? If you see the television antennas, they are generally really on the mountain. They find the hill, and then they put a big tower, and then they put it on the top of the tower. Cell phone antennas have to be closer. The television antennas goes 45 miles, so they just put one in every city. But cell phone antennas, they have to put one every block, so they go to the building top. Yeah.
What does BS and MS mean?
Okay, that's good question. Thank you for asking. BS is the base station, MS is the mobile station. So BS could be the transmitter or receiver, doesn't matter really, and MS is the other end. Focal length is plural of focal length is foci, whatever that is called, right? All right, so now let's see. Radius of the ith ellipsoid at distance dt from the transmitter and dr from the receiver, so this is the thing, is given here, ith ellipsoid. So the first letter should be I. It looks like 1 to me, but it should be I times lambda times dt dr upon this and that, and free space is followed up to the distance up to which the first ellipsoid touches the ground. So basically, if you calculate where the first ellipsoid happens, that is where up to that will give the break point, basically, up to which the formula is d square. After that, it is d raised to 4. All right. So we are just touching the areas of wireless communications, which basically we are getting the essence of it to just understand what happens. So you know basically is that why the numbers are different sometimes. Okay. All right. So next thing is multi-antenna systems. So you don't have to have one antenna. You could have more than one antenna. Right. So you could have multiple receiver antenna. We call it receiver diversity. You could have transmitter diversity, which means multiple transmitting antennas, or beam forming, which is basically directional, and MIMO, which is the multiple input and multiple output. So we'll explain all of those in a minute. So receiver diversity means that you could have many antennas to receive and do something with them. Okay? So you combine them somehow. So this combination could be that, and this sigma simply means that you could just have a logic here which takes the strongest signal, for example, and that is called selection combining. Selection combining is select the antenna with the highest signal to noise ratio. So you calculate the signal to noise ratio here, calculate the signal to noise ratio here, here, and so on and so forth, and take the antenna which is the best right at this minute. Alright, that is selection combining. Threshold combining is select the first antenna with SNR above a threshold. So you don't go to all 20 antennas or whatever, you just find one which has more than 0.7 or whatever threshold you set. Okay, so you set a threshold and find the first antenna whose SNR is above the threshold and you use that signal. So we really haven't combined anything, we have selected so far. Then there is a maximum ratio combining. The phase is adjusted so that all signals have the same phase, and then weighted sum is used to maximize the signal to noise ratio. So you look at the phase of each signal and then you combine them, you change them, adjust the phase, and then you add them together. So this is really combining in some sense. Okay, you add them with weighted sum. And again, there is a lot of mathematics which goes behind it, where people calculate the right weights and the right phase and so on and so forth. But the idea is that with more than one antenna, you can improve your probability of receiving the correct signal. Okay? Same thing you can do the transmitting antenna. You could transmit more than one signal, and then at the receiver you could see where you are getting the best one, and you could do similar combining like you did before. Is you can take the best received signal, or you could take the best phase, or you combine all the phases, things like that, right? And if the channel is known, then you can do some mathematics. So this is where that formula we talked about, channel model, output frequency spectrum equal to input frequency spectrum times the channel frequency spectrum plus the noise. They use that formula to figure out how to combine all of this. And a similar concept happens in beam forming. So what is the beam forming? Beam forming idea is that you keep lots of little antennas So this one shows one antenna here, big antenna, but it's not really one antenna. It is lots of tiny antennas here. Okay? And they are phased. Basically, you send them signals such a phase so that most of the power is in one direction, like here. So most of the power is going here. Okay? There might be a side lobe like that, but most of the power is going here. So this is basically directional. So that way the signal will go to that house of that receiver. Right? And the interesting thing is that all of this can be changed in a microsecond so that it goes to this house without any mechanical movement. It's all electronic phasing thing, right? It can go to this one and then it can go to that one and it can come back. And they do this. This is called beam forming. So basically, you might think you're getting the signal continuously, but you get a signal for a small time. You're doing time division multiplexing in some sense, and it is coming at a very strong power to you and then going to the other persons. Okay, so this picture here shows multiple antennas. I have shown here 3 by 3. It could be 4 by 4. So there are 9 antennas shown here in this one little area, but could be any number there. And the idea is when you have all these antennas, all this multiplication of frequency domain and all that requires Fourier transforms, like we said before. And all that Fourier transform is done in digital signal processing, DSPs, units. And so basically by calculating that, they can figure out exactly, when it is totally aligned. That takes us to the next concept, which is MIMO, which you have heard before, I'm sure. But MIMO stands for multiple input, multiple output. Basically, if you go to buy anything today, it generally has more than one antenna like this. Right? In the old days, just 4 years ago, it used to be just one antenna, or maybe two, but basically only one would be used. So now we have most of the things are multiple antennas. Right? And not only at the receiving or the transmitting, but both ends. So we have multiple inputs and multiple outputs. That is called MIMO. Alright, your base station might have 2 or 3 antennas, and your computer might have 2 or 3 antennas. So even though this one doesn't show any antenna on my computer, I'm sure there is one antenna on this side and there is one antenna on this side. Okay? Inside your little phone, there might be more than one antenna. Alright, so this is called MIMO. MIMO is simply multiple input, multiple output. That means multiple transmitters, multiple receivers, and the transmission is actually done in such a way that you get benefit out of it. The benefit is not really linear to the cost, linear to the number of antennas. So here's the thing. Suppose you have 2 transmitters and 3 receivers. You don't get 6 times. Generally what you get is at least the minimum of the 2. So you get at least factor of 2 here. 2 times 3, minimum is 2. You get at least twice as much throughput or power or whatever you want to call it. And it could be different. Okay, so here is some actual measurement. And this was done at the time of WiMAX. WiMAX is called A22.16. At 2.5 gigahertz, 10 megahertz, TDD, all that. It doesn't really matter to you because we haven't discussed any of this. And so the idea is that if you have 1 by 1, you get 1.2 bits per hertz. If you have 1 by 2, you get 1.8 bits per hertz. If you have 2 by 2, you get 2.8. So you see you have 4 times more antennas, but you get about 2.8 times. Well, you get about 2.5 times more than 1 by 1. Right? And by 4 by 4, you get up to 5.1, which is almost like 4. Okay. Now, if you get more bits per hertz, basically you are getting more bits because for the same hertz, right? Any question about MIMO? So, then there is the last thing that I want to talk about is, which is actually takes us to the discussion of the 4Gs. So the original cell phones when they came out, we call them 1G, first generation cell phones, back in 80s. In 90s we had second generation phones, and in 2000s we had third generation phone, and 2010 onwards we have fourth generation phone. Every 10 years a generation is born. The first generation phone, they're all analog. Analog in the sense that they didn't do 0101 like we do now. You just sent, when you spoke, your analog voice was sent on the wireless waveform. Right? That was first generation. Second generation, and therefore multiple users, if they are using multiple users, they were different only in frequency. So as you can see here, one phone was given a particular frequency. Let's say you might be given 4.1 and he is given 4.2, he is given 4.3, 4.4, 4.5. It's like today we know that in Wi-Fi we have channels 1, 2, 3, 4, 6, 11 and all that. So you use channel 1, you use 11.6, channel 6, you use channel 11, something like that. Frequency division. Alright, that was the first generation. So obviously you couldn't have too many users. Right? So the second generation we became smarter, and we said we will do TDM, time division multiplexing. And we became digital too. Okay, second generation is GSM, which we still use, and it is digital. So basically we take the signal, your voice, convert this into zeros and ones, we sample it, convert into zeros and ones, and we send the sample. Okay, that way actually the voice, once it is gotten back into, it will still be 0 and 1, and there won't be any error because we would have done error checking. So there is less aberration or whatever you want to call it of the noise, of the sound, right? So that is second generation. So first generation was FDMA, second generation was FDMA and TDMA combined. I mean basically one frequency is time division, but you could have many frequencies. Third generation was CDMA. Now we discussed CDMA last time. I don't know how many of you remember still, but that's what it is, code division multiple access. Anybody remembers that? What is that?
You come up with different codes for each of the different users, and then they're able to transmit.
Good. So you can use the same frequency at the same time. So now the thing is all the same, and that is CDMA. The entire world adopted CDMA in 3G in 2000. So whether you are in any country, doesn't matter which country it is or which system you're using, everybody was doing CDMA. That was the latest technology of the time. Okay, but something new came up later on, and that is 4G is called OFDMA. Okay, even better than CDMA. And so 4G, we are going to talk about what is OFDMA. OFDM stands for orthogonal frequency division multiplexing. So it is a frequency division multiplexing, but it is orthogonal. What does that mean? Basically, they noticed that if you have so much band, you don't want to use all of it for every user or for all of it at the same time. So if you are given, let's say, 1 megahertz, you don't want to use all of it at the same time. You divide it into tiny, maybe 1 kilohertz, 1,000 of them, or 10 kilohertz, 100 of them, channels. So each channel is, you still have the same spectrum, but each channel is small. And that is very good, because if you do that, then you can do better. So let's see how you can do better. So I am given this big channel, all right. If I want to send, what will happen is, let's just take an example, 1 megahertz, and I'm going to the coding that I have gives me 1 bit per hertz. So how many bits will I get? 1 megabit. I will get 1 megabit per second, right? So each bit will be how long? If there are 1 million bits in a second, how long is each bit? 1 microsecond, right? I mean, you can calculate if I say how long, you could take the speed of light and figure out how long that is in meters, but let's not go into meters. Each bit is 1 microsecond, right? Now what I do is, instead of that, I convert that into, let's say, just for the sake of simplicity, you won't do this, but well, let me keep it a little bit realistic. So let's say we convert that into 110 kilohertz channel. So each channel now is 10 kilohertz. You see, tiny channels. Now I am still getting 1 bits per hertz, right? I do the same thing. So how many bits I will get through this channel? Channel number 1, 10 kilobits per second, right? And how long is each bit in terms of time? Now you just divide 1 by 1, 10 kilobits, it's like 100 microseconds, right? So the bits are very wide. Okay. Now if the bits run into each other, we have lot more leeway, because if there is inter-symbol interference, if there are two things which are 100 microseconds long, we can lose 1 or 2 microseconds and still have 2 bits. If the two things are 1 microsecond long and we lose 1 microsecond, we have lost the whole thing, right? So in terms of multipath, in terms of inter-symbol interference, it is much better to use these wider bits with tiny channels than to use one channel with tinier bits. Okay, so that's the whole idea of OFDM. So what they said was, when you get a band, you just don't use one spectrum, you use little bit channels. So I have shown here the frequency spectrum of each channel. So this frequency goes maximum here and power goes down. So this is the power actually goes down. So there are different colors, means different channels. Generally, instead of showing this power thing, we just show the impulses. So this is the first channel, second channel, third channel, and thousands of them. Okay. Now the other advantage is that if there is a noise here, suppose you find out there is a lot of noise here, we don't have to use that channel. We can use the rest of it and still get through. Whereas if you had to use the whole channel and there is a noise, little noise here, it will spoil the whole thing. Right? So that is another advantage of having multi-carrier. This is multi-carrier basically, right? Is that instead of one carrier, you have multiple carriers. So the idea is the frequency band is divided into 256 or more sub-bands, and these are orthogonal. So the power level is such that whenever one is maximum, everything else is 0. Okay? So this is called orthogonal. So each carrier is, so where peak of all one is null of the others. Each carrier is modulated with a BPSK, QPSK, 16 QAM, 64 QAM, depending upon the noise. So that's another advantage. That if there is little noise, we use 64 QAM. If there is more noise, we use 16 QAM. If there is more noise, we go down to QPSK and BPSK. So BPSK, remember, with BPSK, if you remember now, you get only 1 bits per hertz. With QPSK, you get 2 bits per hertz. With 16 QAM, you get 4 bits per hertz. So those require a lot more careful looking at the amplitude and phase. And therefore, if there is a noise, that will affect QPSK more than BPSK. So this is basically most resistant to noise, but you get less bits. This is least resistant to noise, but you get a lot more bits through. Right? So you want to use this one as much as possible. So what you do here, you look at all of these and see where there is less noise, you use 64, where there is more noise, you use 16 QAM. So how do you find out where is less noise or more noise? Basically what you do is, you reserve some of these carriers just for that purpose. We call them pilots. Pilots are not used for data. There I send exactly what I know I am sending. So I can just send 010101. The receiver knows exactly what was sent on the pilot, and it can say, oh, the noise is too much. Alright? So some of these carriers are used for pilot and others are used for data. But depending upon the pilot, we know which carriers to modulate with what modulation. Alright? And we can get the maximum out of that channel. Okay? So this is OFDM. Now OFDM is the technology of the day, in the sense that today, if you design any wireless thing, whether it is 4G, or whether it is 802.11 AC, or whether it is 11.N or 11N, it's all OFDM. Anything that you design in 2000, it was all CDMA. Anything that you designed in 1990s, it was FDMA and TDMA. So we basically, so this is the next generation, is the current generation, is OFDM. Okay? It's clear what is OFDM? Multi-frequency, multi-carrier. Alright, so now that you understand, so it is used in AG16 and it is used in digital video broadcast handheld, and it is used in everywhere else actually. It is used in DSL, it is used in cable modem, everywhere else. So the advantage of OFDM, you can easily implement using FFT and IFFT. So Fourier transforms and the inverse fast Fourier transform. Those are the magic actually. How do you transmit a signal into 1,000 pieces? You do that using Fourier transform. Computational complexity is B times log BT compared to the order of B square T for equalization, where B is the bandwidth and T is the delay spread. Now let me explain this whole thing. So B is the width. Now what happens is when you have signal that is so wide, you have to equalize it. Equalize means whenever you process it, there is a variation, right? And the amplifiers and etc., they're not designed to be equally good at all the frequencies. Some of them are, less amplification here, more amplification there, and so you have to equalize those things, right? So it's much more difficult to handle wide signals, much easier to handle narrow signals. So that's what it is saying. B square T, T is the delay spread, and delay spread is simply that idea of, if you remember here, this is the delay spread. You send it here, but this signal is spread all the way up to here. So this is the spread, delay spread, how wide it became in time. All right, so it is now B log BT, which is much less compared to B square T. And graceful degradation if excessive delay. If suppose you go through many paths, that means your delay spread has become very big. This thing doesn't die totally. Robustness against frequency selective burst errors. Now let me explain what that means. Frequency selective burst errors. So first of all, burst error means suddenly there is a big burst of a noise somewhere. Somebody put a hammer or something. In wireless terms. I don't mean a noise. In wireless, signal suddenly came up. And frequency selective means that it just affects a particular frequency, but not the whole thing. It's not everywhere, but it is just here. So if there is somewhere noise, no big deal. So robust against that. And allows adaptive modulation and coding of the subcarriers. Adaptive means we measure the noise and then we change this modulation accordingly. That is called adaptive. Adaptive modulation is either we use BPSK, QPSK, QAM, 4 QAM, 16 QAM, depending upon the noise. That is called adaptive modulation. Encoding. Basically, adaptive modulation encoding of the subcarriers. These are all subcarriers. Robust against narrow band interference. Again, the same thing. This is same thing as frequency selective. Narrow band means interference. Somebody else is transmitting, but they are not using the whole band. They are using some small part of the band. We call that narrow band. Okay, if they are using the whole band, that is wide band. But if there is a narrow band interference. So now there are the two terms we use: noise and interference. Noise generally is due to sources that, basically not expected, that is just noise, right? Interference is when somebody else is transmitting at the same time and they're interfering with your transmission, right? So obviously you have to first take care of the interference, because interference generally is so high, noise is so low, right? So sometimes we say signal to noise ratio, sometimes we say signal to interference and noise ratio, SINR, and sometimes we say signal to noise ratio. So anyway, so narrow band interference, basically all that says is that somebody else is transmitting but they are using part of the band, you can still continue your work. Alright, next. Robust again. Allows pilot subcarriers for channel estimation. So we already talked about that one. Pilot carriers are used for channel estimation. What that means is that we want to figure out where the channel noise is and what the frequency response is. All that we can do with the pilots. Okay, so we covered a lot of stuff here. Any question about any of this? Yeah?
Can you explain more about the complexity of big O B square T?
Okay, so this is order of, right? O is for order of. Everybody understand the complexity? Right? When you measure the complexity of something, you say order of n, means it is proportional to n, as opposed to n squared proportional to n squared and things like that, right? So that is order of. B is the broad is the width of the frequency width, and T is the time. See, so we have two things here. How broad is the channel? B, how many hertz, and T is how much is the spread in the channel. Spread in the channel is not really easy to guess unless you send something and see how many multipaths there are, and then how you send an impulse and it becomes so wide. That will give you the delay spread, right? So that will give you the T. So once you figure out for the channel, so T is for the channel and B is for actually the transmitters, whatever spectrum they are using, BT. So this one is the computational complexity. So when you do this Fourier transform, you have to do computation, right? There are multiplications, division, and so on and so forth in the Fourier transforms. And so that complexity we are talking about is proportional to this thing, as opposed to this if you have to do equalization. Here, we don't have to worry about equalization because the channels are so small that we don't have to worry about equalization. But there, you have to do equalization because the amplifiers do not have constant amplification.
But we still have to equalize the signal, right? Before the computational thing.
Oh yeah, right. So hold on. The amplifier, if you have 10 kilohertz channel, you can find a good amplifier that will just keep it for 10 kilohertz constant. But if you have a 10 megahertz channel, it's very expensive to find an amplifier that will keep constant amplification. Okay, so it's just basically, how wide is the amplifier's response.
And also, if the subcarriers are very small, then equalization may not really be required.
Yeah, right, because there is very small difference. Okay? Alright, so design consideration. So now the question is, Can we just use a lot of carriers? Why stop at 10 kilohertz? Remember I said, first I said 1 kilohertz, and I said, no, let's keep 10 kilohertz, because that is what is generally used. And the reason is, if you have lot of carriers, then you will get per small data rate per carrier, which doesn't really matter. But the thing is, you get large symbol duration, which is really good, because you have less symbol interference. So it's good to have thousands or maybe 10,000 carriers. All right, but what happens is, if you have too many carriers, then the carriers are next to each other, right? And now there is a Doppler shift. Remember, Doppler shift is that if you move little bit, the frequency changes. So this frequency becomes that frequency. So you have to worry about both. You have to worry about time and you have to worry about frequency. Time wise, it is very good, because your symbols are so big, and you won't have any inter-symbol interference, but you have inter-carrier interference. Alright? So what will happen is, reduced carrier spacing means increased inter-carrier interference due to Doppler spread in mobile applications. Alright? So every technology, when it is designed, the cell phone technology, they decide how fast can people move. So if the technology is designed for walking, you can just walk. You cannot go in the car. But right now everything is designed for cars. That means up to 120 kilometers per hour or 60 or 70 miles per hour. That is speed. If you go faster than that, then it may not work, because of the Doppler shift. Okay? Easily implemented in discrete Fourier transform, that's fine, and fast Fourier transform, etc., etc. So these are the two things. So let me tell you why I'm telling you all this. For example, at one point I was designing a technology for planes. Now, can you imagine, planes are going to go 5, 10 times, 100, maybe 10 times faster than the cars. So even 10 kilohertz, would cause a lot of intercarrier interference. Right? So the speed matters. So this is basically a trade-off between intercarrier versus intersymbol. Now you understand both. Intersymbol is how wide is the symbol in time. Intercarrier is how wide is the channel in frequency, and how fast they are moving. All right. Then we talk about OFDMA. So the next term we use instead of OFDM is OFDMA. OFDMA, MA stands for multiple access. So OFDM is the modulation or multiplexing, one of the two, but this is multiple access. Multiple access means if you have multiple users, they want to use the same band, how do they use it? Do we give them in time? Do we give them in frequency? Do we give them in combined? And so initially what they did was, when they discovered OFDM, they said, okay, all right, we have 1,000 frequencies. So user 1 gets all 1,000 frequencies, then user 2 gets all 1,000 frequencies, then user 3 gets all 1,000 frequencies. So that would be like TDM. Right? We are going to do OFDM with TDMA. Multiple access is time division. Modulation is OFDM. But then they said, no, we can do better. And the better is that we do both TDM and FDM. So the user 1 gets these carriers for this much time. User 2 gets the same carrier for the next time. User 3 gets these carriers for this time. User 4 gets... So you can draw any rectangle anywhere. And so this is what we did in WiMAX. This is used in WiMAX. So when we have to schedule, scheduling is a research problem, and we did quite a bit of work in research, in scheduling research in WiMAX. And the idea is, how do you fill up this rectangle with small rectangles? So you know how much each user needs, and you have to fill up this whole thing available to you so that it is optimally filled with nothing left. That's the problem. Right? Those are the kinds of the problems that we networking guys deal with, and we don't have to worry about knowing the details of the mathematics underneath. We can just do the bucket filling thing. Right? So this is the idea, is that we we give each user a certain number of frequency for a certain amount of time, and so each user gets a rectangle, and we have a certain amount of rectangle available. So this is called OFDMA. OFDMA is multiple access using OFDM. Okay. Now the last term I think is SOFDMA. So this term appeared, actually we are just preparing a lot more for WiMAX because we used all of this in WiMAX, but when we were designing WiMAX, the problem was that some countries had only 1.25 megahertz available, other countries had 3.5 megahertz available, other countries has 5 megahertz available. Every country had a different band available, different width available. So are you going to design a equipment for each of these countries, or can you design something so that it works in all the countries? Okay. So then they came up with a concept that, okay, really what we should do is we should standardize such that the same equipment can be used in all the countries. And that version is called scalable OFDMA. And let me explain, I will explain to you what scalable means here. But basically, the carrier spacing determines the symbol duration. What that means is that if you divide into 100, you get some duration of the symbol, right? How wide the bit is. If you divide into 10,000, you get smaller and smaller. So the carrier spacing, basically the carrier width, the carrier spacing determines the symbol duration. So symbol duration is carrier spacing, and the subcarrier spacing basically is equal to the frequency that is given to you, the band divided by the number of the subcarriers. So what we do is we keep the symbol duration constant, because most of the electronics that you have basically depends upon the symbol duration. If you keep the symbol duration at 100 microsecond, then your electronics will remain the same. But if you need somewhere 10 microseconds, somewhere 100 microseconds, you need different electronics, right? So if you want to use the same electronics, the idea is that you keep the symbol duration constant and you change the number of carriers in every country. So basically what happens is the standards, whether it is 11N or whether it is WiMAX or whether it is LTE, all of them use OFDMA, they keep the carrier spacing fixed to 10.94 kilohertz. Well, okay, hold on. 10.94 is not universal constant. 10.94 is what is used in FTD, in WiMAX. Okay, I haven't checked in LTE how much it is, but it will be close to that. And similarly, I haven't checked what is in 11N. So they keep whatever frequency they select spacing, and that fixes the symbol duration, right? And they just change the number of carriers. Number of carriers depends upon how much is available. If you have 1.25 megahertz and your spacing is 10.94, you can just divide 1.25 by 10.94 and you get something like this is 1000 divided by 10 is 100. You get about 100 carriers, right? For this one you will get something like 300 carriers. For this one you will get 500 carriers, and so on and so forth. So that way you can use one equipment in all the countries. So this version of OFDMA, where we don't know the number of carriers, that depends upon how much spectrum you have, that is called scalable OFDMA. Alright, so I said something and I want to make sure that you understand that. That the carrier spacing, which means basically we said the width of that little carrier, that is the carrier spacing, that determines how wide your bits are. That is called the symbol duration, right? So the symbol duration is determined by the carrier spacing, and that we keep fixed. That's all. And then we find out the number of carriers. But we have shown here some blue things and some black things. And basically the black ones are data carriers, and the blue ones are pilots, right? So if you have little, you will have just one pilot. If you have bigger channel, you get many pilots. That brings us to the end of today's lecture and the 5 key points to remember. First thing is that the path loss increases at a power of 2 to 5.5 with distance. Remember, it was d square up to a certain point and it was d raised to 4 after that point. And that's an approximation. In the real world, it could be anywhere from 2 to 5.5. Right? So you have to go to and measure it in the practice. And people have done this in all the cities. But for us, for theoretical guys, we just keep it 2 up to a certain distance and 4 after that. Fading means changes in the power. So that is what we call fading. It's the power loss, right? Fresnel zones. Now you know the Fresnel zones, those ellipses. More clearance you have, more ellipse can pass through, the better signal you will get. Okay? Any obstruction in the Fresnel zone will cause increase the path loss. And then we talked about multiple antennas. So you could have receiver diversity, transmit diversity, you could have smart antennas, which are basically those beam forming, and you could have MIMO. Then we talked about OFDM. So that adds to our list of TDMA, TDMA, FDM, and CDMA. Now we have OFDMA. And OFDMA means that we draw those rectangles. Okay. Any question about any of these? If not, then we have a homework. So let's see. The first part says determine the mean received power at subscriber station. As a subscriber station, the channel between the base station at 14 meter and the subscriber station at 500 meters. So we are showing you the heights, 2 heights. The transmitter and the receiver gains are these in dBs. Now remember, everything that is given to you in dBs, when you multiply or divide, you cannot multiply in dBs. Okay? So you have to convert that into some ratios when you multiply. dBs only add, right? If you have to add sometimes, then you add dBs. But if a formula calculation requires multiplication or division, that means you have to convert. Use a power exponent of 4. All right? Transmitted power is 30 dBm. Now again, I give you power in dBm. If you are going to multiply it, you have to convert that back into watts. So this is basically using that formula which has HT, the height of the transmitter and the receiver. Okay. This one is OFDM problem. With a subcarrier spacing of 10 kilohertz, and I have kind of rounded it up, 10.94 10 kilohertz, how many subcarriers will be used if you have 8 megahertz channel? All right. And what size of FFT will be used? So FFTs do not come in every size. FFT come in the power of 2s. So you have 64, 120, 64, then generally 256, 1024, things like that, right? So if you need 900, you go to 1024. In a scalable OFDM, the same thing now. Basically, you have 3 different bits given, and then you just calculate how many you will need for each of them.